Okay, we're going to look first at a theorem. It's called Raleigh's theorem, and you don't need to memorize this one. You're not going to be tested over it, but we're going to use it a little bit later today, and it's good to know, and it makes sense, I think. So it says, if f is a continuous function on a closed interval a to b, so we've had other theorems that have started this way, and it's also differentiable on the open interval ab. So you can take a derivative at all points on the interior. You obviously can't take derivatives at the two endpoints. Okay, and it says if f of a and f of b are equal. Okay, so let me draw a quick picture of what that looks like here. You have some point on the graph, a f of a, and some point b f of b, and they're saying that the y values at a and b are the same. Now, we don't know what happens in between those points, okay? So I can't draw the rest of the graph, but let's see what it says here. Then there must be a number c between a and b, so there has to be a c somewhere in here, such that f primed of c equals 0. So the derivative at this point c has to be 0, which means the slope of the curve is going to be 0 there, and therefore the graph will be flat. Okay, so let's take a look real quick at the three possible cases that could occur in this situation and gain some, I guess, acceptance that this is a true theorem. Okay, we're not really going to go deep into the proof here, but this is just going to be a quick appeal to your reason proof. Okay, case 1 says that after a f of a, this graph is going to initially increase. Okay, and I don't really know what happens after that, but initially increases. Now, to get from a f of a to b f of b, this graph has to at some point start to decrease and head back to b f of b. It may dip below both f of a and f of b, we don't know, but at some point it has to start to come down. Okay, and when it starts to come down, there's going to be a local maximum. And the slope at a local maximum, if your derivative is defined, which our derivative is defined by the hypotheses of the theorem, says that the derivative there has to be equal to 0. Okay, same thing's going to happen over here. If the curve initially decreases, then at some point it has to come back up to end up at b f of b. When it does, you will have a local minimum, and at this point there's going to be a slope of 0 because the derivative is defined for all real numbers. And we learned last class that the theorem says that if there's a local min and the derivative exists, the slope there is going to be 0. And then the last case is kind of the not so exciting case, but it's a possibility, and that is the case that the function is constant for the entire interval. Okay, so you draw a horizontal line that goes from a f of a to b f of b, and obviously since this is a constant function, f prime of x is equal to 0 always. So there's multiple values of c where the derivative is equal to 0. Okay, this theorem guarantees you at least one of those such points. Today's lesson is on a different theorem, which appeals to our intuition. Okay, so you're going to go through a little scenario here. In Pennsylvania, there's this thing called a turnpike. So you get on the turnpike, you get a ticket that says where you got on and what time, and then you get on the turnpike, and whenever you get off, you approach a toll booth and you hand in your ticket, and it tells you how much you have to pay. Okay, so obviously the different cities, they know how far apart they are. So this driver turns in his ticket at the toll booth, and the toll attendant gives him a ticket for speeding right away. Okay, the driver asks for a reason, and this is the answer he gets. Okay, it says you got on the toll road at 2:13 p.m. because the ticket says so, and you got off at 3:08 p.m. because I just took your ticket and I can tell. I quickly did a calculation in my head, and your average speed was 76.36 miles per hour. Okay, and we'll assume that the speed limit on the Pennsylvania Turnpike is 70. So he says your average speed was 76.36 miles per hour. That means you had to have been going more than 70 at some point during your trip. And I think we'd all agree that this is a true statement, right? We believe this, okay? But there's some mathematics behind why this is true, okay? And in class last time, you got to play with a GeoGebra thing that's related to this, so we'll talk about that in a second. So the theorem we're going to talk about today is called the mean value theorem. Okay, mean here is meant in the mathematical sense of an average. Okay, so we've had the intermediate value theorem, the extreme value theorem, and then this is the third of the three value theorems. It says if your function is continuous on a closed interval ab, so the other two value theorems have started this way, this one adds and is also differentiable on AB. So this starts off like Raleigh's theorem does. Okay, then there is a point C somewhere between A and B such that this is true. Okay, now what does this say? F of B minus F of A over B minus A. That we should recognize as the average rate of change, the AROC, okay, of our function f on an interval AB. In other words, is the slope of the secant line. Okay, this number, it has to be equal to the derivative at some point C that lives between A and B. And this we'll interpret as the instantaneous rate of change of our function f exactly at point C. So as far as the police officer was saying, your average speed has to equal your exact speed. Verbally, we'd say the average rate of change must be the same as the instantaneous rate of change at least one time, maybe more. And if we do this graphically, we're saying that the tangent line has to be parallel to the secant line at some point. And that's what you play with in class. We had a curve, and I labeled 2 points on the curve, and I connected those 2 points with a line, that's a secant line, and I asked you to try to drag the sliders so that you could create a tangent line that was parallel to that secant line. And you were able to do that, but only with the two functions that were both continuous and differentiable. Okay, and that's why the hypotheses have to be satisfied. Now, I'm going to prove this theorem at the end of the video. If you're interested, it'll be on a yellow slide. You're not responsible for the proof, but it's interesting where it comes from. Now, to help us remember the whole part of this theorem, there's a song. So I'm going to pull up some music that goes with these words, and you can follow along, and I'll try to drag along with the cursor. So let's jump into some examples. One of the things you're sometimes asked to do is to find this mysterious value of c that lives between the two endpoints of the interval. Okay, so here's my function f, here's my interval a into b, -1 to 1, and they're asking me to find this value of c. Okay, and then we're going to graph the curve, the secant line, and the tangent line to verify that we got it right. Okay, first of all, make sure f is continuous and differentiable. In this case, we have a polynomial which is continuous, and its derivative is also polynomial, so differentiable. The mean value theorem can be used. Okay, not all functions have the mean value theorem applied to them, so be careful there. Okay, so what do we know? We are told that if you take the average rate of change on the interval, so let's figure out what that is first, f of 1 minus f of -1 over 1 minus -1. Okay, what is f of 1? F of 1 is 1. F of -1 is -1, and 1 minus 1 is 2. So we're going to get 2 over 2, or 1. Okay? The theorem says that this number is equal to f primed of c, for some c that lives between -1 and 1. Okay, so what is f primed of c? Well, in this case, we have f primed of x is equal to 3x squared. And so therefore, f primed of c would be 3c squared. So I need to solve the equation. 3c squared equals 1, and my answers have to live between -1 and 1. I'm a guaranteed 1, but there could be more. So I'll get 1/3 is equal to c squared, and c will be the positive and negative square roots of 1/3. And the square root of 1/3 and my negative square root of 1/3 will both live between -1 and 1, so there's going to be 2 spots on this curve where the tangent line is going to be parallel to the secant line. Let's take a look. Okay, so let's start with our function f, which is x cubed, and we're going to go ahead and draw a line that goes from -1 f of -1 to 1 f of 1. Okay, that's the secant line that we talked about here, and let's label our points. Okay, so a is -1 f of -1 there, and b is going to be 1 f of 1. Okay, I'm going to zoom in a little bit here. Now, we said there were 2 spots where the tangent line should be perpendicular to the secant line. I'm going to ask this to find the tangent at 1/3 to the 1/2, so that's the square root of 1/3 to the graph of f. And GeoGebra can handle that, and there's the line that's tangent at the square root of 1/3, and it looks in this picture to be parallel to the secant line. All right, let's also check the other one. So we have tangent at negative 1/3 to the 1/2. That's the negative square root of 1/3 to my graph of f. Okay, and there's another tangent line that is parallel to the secant line. Okay, another application of this theorem that comes up a lot in AP questions is to analyze data given to you in a table. So I've made up a fictitious function and given you some table values here, so let's see what this says. It says stress level, which is measured in fictitious units called tantrums, is a continuous and differentiable function of time. Okay, so S of t is continuous differentiable, the mean value theorem applies. Okay, a person is considered stressed out, in quotes, if their instantaneous rate of change of stress level is ever 20 tantrums per minute or greater. So if their S primed of t is ever greater than or equal to 20, a person's considered stressed out. Okay. Using the data in the table, argue whether this person is ever stressed out during the interval given. So here we have t, time measured in minutes. Okay, so this used to be an old class period, 85 minutes long, I suppose. And this is the number of tantrums that have occurred in the 90 minutes, okay, or in the 85 minutes. So at the end of 85 minutes, there's been 666 tantrums. At 77 minutes, there had been 400 tantrums, etc. Okay, now, we don't have a function to take a derivative of, so I can't really calculate S prime of t and set it equal to 20 and do things like that. I have to use a theorem to connect S primed to values of S. And the theorem that you use is the mean value theorem. So what you're looking for is, you're going to say that this is true if I can find an interval where S of b minus S of a over b minus a is greater than or equal to 20. If I can find that, then the mean value theorem says that these two numbers, S primed of t and S of b minus S of a over b minus a, have to be equal. So that's what I'm going to search for. And what I'll do is pick different pairs of numbers in this table and find their average rate of change between those two pairs. So I did that for a few. Let me make this a little bit bigger so you can see. Okay, so for example, the first two, or the first three, I guess, I did 80 minus 40 over 17 minus 10. That's the first two ordered pairs, and I get an average rate of change of 5.714. That's not big enough. Then I did 99 and 80, and I got 1.727. That's not enough to be considered stressed out. So then I went down a ways and I checked 77, 400 and 59, 180. Their average rate of change came out to be 12.222. So that's closer, but still not enough to be considered stressed out. Okay. Finally, on my fourth try, I found the last two ordered pairs, 85, 666, and 77, 400, to have an average rate of change of 33.25. That's bigger than 20. Okay, and so now I can use the mean value theorem to conclude that this person would be stressed out. And let's write up how this would be worded formally. Okay, so I'd say since S is continuous and differentiable, I'll abbreviate here. Okay, the mean value theorem applies. Your readers are going to want to know that you understand the hypotheses of the mean value theorem, so it's important to state that at the beginning. Okay, now since 666 minus 400 over 85 minus 77 equals 33.25 by the mean value theorem, that S primed of t has to equal that number, 33.25, on the interval that we use to find the average rate of change. So on the interval 77 to 85. So somewhere towards the end of class, this person was having enough tantrums per minute to be considered stressed out.